Hi everyone, welcome to Physics 151 Lecture 14B. As we continue our discussion of force and dynamics, we're now going to cover the force that comes from friction with a surface. So when an object is in contact with a surface, it can experience either static or kinetic friction, depending on whether the object is at rest or in motion. This is also in contrast to other types of friction, like fluid drag, which includes air resistance. That follows different formulas, and we're not going to cover that quantitatively in this lecture. In this lecture, I'm also going to use an example problem from tutorial 14B, and there will be additional friction problems in online homework 14 in Mastering Physics. So let's start off by talking about the direction and the magnitude of the force that results from surface friction, from the contact of an object with a surface. First of all, the direction of the friction. Okay, that direction is always going to be parallel to the surface. So whether it's static or kinetic, the direction of the friction force will always be parallel to the surface of contact. And second, depending on whether it is kinetic, if the object is moving, then the direction of the kinetic friction force will always oppose the direction of motion. So that means it's always opposite to the direction of the velocity. Not the acceleration, not the displacement, but the velocity. That's the direction of motion. If the object is at rest, then the direction of the friction force will always oppose the direction of the other net forces that are acting on the object. So the static friction force looks at the other forces that are trying to make the object move and then opposes the direction, their net direction, to try and keep the object at rest. So that's how we decide what direction the friction force will act for either case, kinetic or static. Finally, how do we decide how strong that friction force is? That's the magnitude of the force. How many newtons is it? Well, let's talk about the kinetic case first. In the kinetic case, in other words, if the object is in motion, sliding along the surface, then the static friction will always, the kinetic friction will always have one constant value, which is equal to mu, the coefficient of kinetic friction, times the strength of the normal force. Now notice this does not depend on the speed of the object. So the object could be barely moving or it could be sliding very fast. It doesn't matter. The number of newtons of the kinetic friction will be exactly the same. Static friction is a little different, on the other hand. Static friction is to put it casually, static friction is lazy. It will only exert as many newtons as it needs to exert just to counteract the other forces present and keep the object at rest. So in other words, if there are no other forces present, no other net forces present, horizontal, parallel to the surface trying to make the object slide, then the static friction will simply be zero. However, if there are other net forces present trying to attempt to make the object slide along the surface, then the static friction can have any value, any magnitude up to this maximum here. So this is a maximum value that the static friction can have. And in fact, if the other net forces that are present are in excess of this maximum value, then the object will break free because the static friction cannot keep the object at rest. So in that case, the object will break free, it will start to slide, and we immediately switch over from the static case to the kinetic case. So that means that the magnitude of the friction force that you're dealing with will suddenly switch from this maximum static friction value to this kinetic friction value. Now I should point out that these little equations here are not, these are not vector equations. These two equations right here for the magnitude of the friction force are both magnitude only equations. In fact, the direction of the normal force, as you probably know, is perpendicular to the surface, but the direction of the friction force, be it either static or kinetic, is parallel to the surface, as we just discussed before. So these are exactly right angles to each other, right? Let me say it again. The friction force is parallel to the surface, whereas the normal force is always perpendicular to the surface. So these are not vector equations, but they are just relationships between the magnitudes of the forces. And then finally, if we look at these equations a little bit more, we see that the units for force are the same on both sides, newtons and newtons. So therefore, the units of mu, the coefficient of friction, must be dimensionless. They have to be, it has to have no units, in other words. Finally, just to sort of keep things realistic, if we could think about what some of the typical values are for mu in real life. I'll come back to this slide in just a second. So typical values for mu in real life have been measured in the laboratory. They've just been tested empirically. We don't have a formula for this. And what you can notice by looking at these values, there's static friction on the left, kinetic friction on the right. If you look at these columns of values, typical values for things that are kind of slippery, like for example, ice on ice or Teflon, look, they're in the range of about 0.01 to zero point 0.1. Whereas things that are sort of everyday objects like wood and metal are in the range of zero point 0.1 to 1, and things that are pretty grippy like rubber on a dry surface are in the range of about 1 to 5. So the ideal sort of frictionless case, if you had absolutely no friction at all, that would be mu equals 0. That's ideal, right? It doesn't really exist in real life, but as you can see by these values of mu near the bottom of the table, that sometimes the values can be quite small. So, but we can, frictionless, the idealized case would be mu equals 0. And then finally, something that is completely fastened in place. So an object that's glued to a surface would be mu of infinity. That would be something that no matter how hard you push on it, it will never ever move. So, however, you notice that you're not likely to encounter values of mu that are in the tens or hundreds or thousands. That's very atypical. The typical values of mu are going to be somewhere between zero point zero 0.01 to zero point 0.1 for slippery things, and then zero point 0.1 to 1 to 5 for pretty grippy things, for pretty grippy situations. There's two more things to sort of notice here. Um, First of all, notice that the values in the static friction column are consistently larger than the values in the kinetic friction column. For a few of these values, they're kind of exactly the same. And Teflon, in fact, is famous for having a static friction coefficient that is very similar to the kinetic friction coefficient. So things that are Teflon coated don't tend to be stuck in place. They tend to smoothly transition from being at rest to being in motion. But apart from that, for everything else, it seems that the value of the static friction is always bigger than that of the kinetic friction. Now, there is a theoretical reason for this. We all know this from everyday life, that objects that are at rest are harder to get moving. You have to push harder on them to get them moving. Then if you have an object that's already sliding, you don't have to push as hard on it to keep it moving. The sort of theoretical reason for this is twofold. One is when an object's at rest, the little peaks and valleys and nooks and crannies of the object will be able to settle in to the peaks and valleys of the surface in a way that an object cannot when it's sliding. And second, weak chemical bonds can form between the stationary object and the surface, like van der Waals forces and dipole-dipole bonds, induced dipoles, things like that. Um, that they, that have less of a chance of forming when the object is sliding. So those are the reasons that an object that's stationary has a sort of stronger grip with the surface in general than an object that's moving. So this is a consistent thing. Static friction coefficients are always larger than kinetic coefficients of friction. And then the other thing to notice about this table is look at what it does not depend on. The only thing that's listed here in this table is the two materials that are involved. So what the surface is made out of and what the object is made out of. So you can have a fairly grippy object like a tennis shoe or a car tire, or you can have a fairly grippy surface like a rubber floor or rubber mat or something like that, or both. So it depends on the both the object and the surface, the two things that are involved. But what is not in this table is the area of the object and the surface. Doesn't depend on the mass, it doesn't depend on the speed. The coefficient of friction depends only on the substances. Now, of course, there's a range of different types of wood. There's a range of different types of metal. You can polish wood to greater or lesser extents. And so, et cetera, et cetera. So notice that these typical values in this table are listed to only like one decimal place, right? One significant figure. Um, and for a specific piece of wood or a specific surface, you could potentially measure the value of mu to greater precision and have maybe two significant figures. But as far as like categories of metal and wood or something, there's quite a range within each of those broad categories. So if we return to the previous slide, a couple of these things that I've mentioned already are just summarized. First of all, the coefficient of static friction is always going to be greater than the coefficient of kinetic friction, as we just discussed. And then, as I talked about on the first slide, the strength and the direction of static friction can vary, as opposed to the kinetic friction, which will always be fixed, fixed in magnitude at mu k times normal force. All right. So at this point, let's take a look at a sample problem. I'm going to switch to my desktop camera. I'm going to take problem number 4 from our tutorial sheet and just use this as an illustration of calculating some coefficients, calculating some forces and accelerations for a problem that involves both static and kinetic friction. So first, let's just take a sort of overview of the whole problem. We have a box with a certain mass that's given at rest on a level table, okay? And that's important in this case because that will affect our calculation of the normal force. And we're given the coefficient of friction for static and kinetic cases between this box and the table. And if we look ahead at what the questions actually ask down below, you're given a series of situations here where you, as a person, can exert some amount of external horizontal force on the box. Initially, you exert no horizontal force, and then you exert, no horizontal force, and then you exert a force of 50 newtons to the right, and then 80 newtons to the right, so you push harder and harder, and then finally 120 newtons to the right. At each of those cases, I then pause and ask, how big is the friction force that arises in response? And what will be the motion, specifically the acceleration of the box, as a result? To help us out, because there isn't much room here for calculation in this part of the page, to help us out initially, I ask for a few sort of preamble calculations at the top. What's the normal force on the box? Because notice that never changes with all of these situations down below. All of the forces that the person exerts on the box are all exactly horizontal, so they don't affect the value of the normal force. There's no vertical component. And then what will be the maximum value of the static friction possible? And then what is the value of the kinetic friction, regardless of the speed, once the object actually starts to move? So let's calculate those three quantities as sort of preliminary quantities. Okay, so these are all sort of preliminary calculations. So first, for the normal force, if we just take a look at this object, if we sort of treat this as a little bit of a free body diagram over here, right, then we can see that there's going to be a weight for the object, which acts toward the center of the Earth. And there will be a normal force acting on the object in response to that from the table. And then as we gradually, we don't have it quite yet, but as we gradually push harder and harder, there will be a force from the person pushing to the right. And then some kind of friction force will probably arise then to the left. I'll go ahead and just draw this as a solid vector. Okay, so the lengths of these vectors here, these two, are going to vary. But at least this will show us roughly with a picture what direction they act. So there's a friction force. By the way, most textbooks will use a lowercase f for the friction force. And this is going to be either static or kinetic, depending on the situation. So by inspection, we can see that in the vertical direction, because there are no vertical components to any of the other forces except for the weight and the normal force, we see that the magnitude of the normal force in this case is just equal to the magnitude of the weight. So I'm just going to skip writing out Newton's second law and all the y components of the forces and just jump right to the result. Okay, so in this case, the normal force will be equal to m times g. And let's go ahead and calculate what that is for a 12 kilogram box. And my calculator tells me that the answer is 117.6 newtons. Now, this is a handy value to have because, as we saw before, the normal force shows up over and over again in these formulas for the friction force. All right, notice how I'm keeping extra significant figures. That's always valuable to do for intermediate values. All right, second, what's the maximum value of the static friction force? So the maximum value of the static friction, and I'll write it like this, was the equality. So you remember that the equation said that static friction can have any magnitude from 0 up to this value. So the maximum value of that equation then is the equality. So that'll be the maximum value right there. So that's going to be equal to 0.850, which is the coefficient of static friction. And then we've already calculated the normal force, so now I can borrow that from the previous line. And that's going to be 99.96 newtons. Again, keep extra significant figures for now for these intermediate values. And then finally, what's the magnitude of the kinetic friction force? Well, it's always going to have the same value regardless of the speed of the object. And that's 0.55. My calculator tells me that that is 64.68 newtons. Okay, so if the object is sliding, if the box is sliding, regardless of the speed that it's sliding with, the strength of the kinetic friction force will just be 64.68. All right, so these are really handy preliminary values to have calculated. So now let's go ahead and consider these different situations down below. So if Fp is equal to 0, so this means that the force that the person is exerting is equal to 0, then what will be the magnitude and direction of the friction force? And I didn't want to say whether it's static or kinetic. I want to let you decide. What is the magnitude and direction of the friction force acting on the box? All right, well, if there is no horizontal external force from the person, and these forces have no horizontal components, then static friction, it's a lazy force. It won't arise at all. So if there's no net horizontal force, I should be clear and say net horizontal force, oops, then that means that the magnitude of the static friction force is just going to be 0. So it has no direction. Right? So we don't need to specify a direction when a vector has 0 length. Now let's start pushing to the right. So we start exerting a force on the box to the right. So for part C, it says that we push to the right with 50 newtons of force here. What will be the friction force, magnitude, and direction as a result? And will there be any acceleration of the box? Well, we know that as we push to the right, stronger and stronger, the static friction grows stronger and stronger to the left, right? It looks at the sum of all of the other horizontal forces on the box, and it grows in response to try and balance out that sum and cause the box to have 0 net horizontal force. What's the biggest value the static friction can reach? It was almost 100 newtons, so just shy of 100 newtons. So if we push to the right with only 50 newtons, then the static friction force will arise with 50 newtons in response, and the box will remain at rest. Okay? So that means that the static friction, so the force of the person is 50 newtons to the right. Sorry, I dropped a sig fig there, but okay. Which means that the static friction force will be 50 newtons to the left. Now let's increase our horizontal force to 80 newtons. If I increase the force to 80 newtons horizontally, then what will the static friction do in response? The static friction can grow up to almost 100 newtons. So 80 is still short of the maximum. So that means it's going to be, situation D will be just like situation C. If we push with 80 newtons to the right, then that means that the force of static friction will be 80 newtons to the left. And the box will still remain at rest, right? Finally, the final case here is going to be enough to exceed the static friction, won't it? If we push to the right with 120 newtons, then we know that the maximum possible static friction force is 100 newtons to the left. So, right, if we, as we're pushing to the right, as we exceed that 100 Newton limit, then all of a sudden the box will break free and start to move to the right. Now, as soon as that happens, we can immediately switch from the static friction case to the kinetic friction case. So now, all of a sudden, our free body diagram is going to look something like, it'll look something like this. Here, I'll sketch it right here. Of course, we still have the weight and the normal force, but we're not very interested in the y components. So now we're going to have a force of a person pushing to the right with 120 newtons, and then pulling to the left, we're going to have only this 65, almost 65 newtons of static friction right here, of kinetic friction right here. So this is only going to be 64.68 newtons. So you can see that there is now an imbalance of the forces in the horizontal direction. There is a net force to the right. So that tells me from Newton's second law that this object's going to accelerate to the right. So we can calculate what that acceleration now is. So let's say, all right, we're going to add up the sum of the forces in the horizontal direction. I don't have a whole lot of room on the page here, so I'll just squeeze it in down here at the lower left. The sum of all of the horizontal components of all the forces acting on the box will give rise to an acceleration of the box. Okay, so this is Newton's second law. The x components of all the forces, weight and normal force add nothing, and then I have the person pushing to the right in the positive x direction, and to the left in the negative x direction, we have the kinetic friction. Now we've already calculated what this value is up in the preliminary part. So that's great. We can just plug that in. I'm sorry to squeeze this work in now. So I'm going to continue over here now to the right. So that means on the left-hand side of the equation, there's 120 newtons of the person pushing to the right, minus 64.68 newtons of the kinetic friction dragging to the left. This is going to be 12 kilograms times the acceleration. So notice on the left-hand side of this equation, then we have 55.32 newtons net force to the right. And we can calculate that the acceleration then is going to be 4.61 rounding now rounding to 3 sig figs, because this is a 3 sig fig value. And the fact that this is positive, right, and that was positive, net force to the right, acceleration to the right, assuming that we've defined the positive x direction to be to the right. All right, so to actually answer the question, the friction force, right, the friction force is going to be 64.68 newtons to the left, because that's now the kinetic friction. And the acceleration of the box is now going to be 4.6 meters per second squared to the right. By the way, this is just to sanity check our answer, this is a really fast acceleration, right? A 12 kilogram box is about a 30 pound, well, it's between 25 and 30 pounds as far as a box. But this is a very fast acceleration, okay? This is gaining something like 10 miles an hour every second. So what would happen in real life is you push really hard on the box to dislodge it and get it to start to slide. But then we would quickly afterward, after just a few moments, a fraction of a second, we would probably decrease our pushing force to be something much closer to the amount of the kinetic friction, which would allow us to slide the box with very little acceleration or nearly zero acceleration, which would be a constant speed. So that's what we tend to do in real life. We push really hard to overcome the static friction, and then once the object is dislodged, then we give it a little bit of velocity with a little bit of extra force. So we accelerate it briefly, and once there's this relatively slow velocity, we'll scale back our force to just match the kinetic friction. And from that point onward, we push it with a constant speed. All right. So with that, I'm going to that's the end of this lecture with that example. I encourage you to return to the tutorial sheet and try example 3, which is somewhat similar to this problem, right? This was problem 4. And questions 1 and 2 are just sort of brief little review questions. And then to also try the friction-related problems in Mastering Physics.